Today's lecture is on inductive reasoning. We've been working on formal deduction for the past few weeks, and this will be a breath of fresh air for some of you. And so the subtitle here is the logic of uncertainty, and that is in comparison to deduction, which can be thought of as the logic of certainty, since conclusions can be established necessarily. So let's remember deduction versus induction. Deductive arguments attempt to provide absolute support for their conclusions. So as I mentioned, the conclusions can follow necessarily. And if you have a deductive argument that is valid, in other words, it has a good inference, and as all true premises, it's sound. So think back to that chart breakdown of deduction versus induction. That's sort of what I'm recapping here. Inductive arguments, on the other hand, at best can show their conclusions are extremely likely to be true. They offer probabilistic support. If you have a good inductive argument, then it's cogent, and that means that the inference is good. In other words, it's strong, and all true premises as well. So whether it's deductive or inductive, if it's going to be a good argument, it has to have all true premises. And then it's just a matter of the inference. Is the inference valid or strong? Okay, so this should say two important kinds of inductive arguments, so the arguments got cut off. The first is an argument by analogy. So let's start with an example. Let's say that you are a parent and you have one kid and one on the way. And so your firstborn learned to talk at 18 months, which someone recently told me is very late. So that shows how little I know about when infants start to talk. But let's just say that your firstborn learned to talk at 18 months, and so you reason that your secondborn will probably talk around then too. You're making an argument by analogy. You're comparing your firstborn to your child that's on the way. Here's another inductive argument that is by analogy. Let's say that you're a surfer and you go to one surf spot, let's say it's called Cowles, and the water temperature there is 55 degrees. So you reason that at another surf spot, call it the Hook, that it will be about that as well. So in both of these two arguments, we have a comparison between two things. An analogy in the first one between the firstborn and the secondborn, and in the second argument, a comparison or an analogy between surf spot 1 and surf spot 2, namely Cowles and the Hook. Let's continue on. Suppose someone's really good at electric guitar, this person named Ned. You could make draw an analogy to how well they would do on an acoustic guitar. It's like, oh, well, he's really good at electric guitar. I've never seen him play acoustic, but I'm guessing because the two instruments are so similar that he would be good or she would be good at acoustic as well. So notice all of these start with something that we know about and then extrapolate to something that we are guessing about. So in the first argument, we know about the firstborn. In the second argument, we know about Cowles. And in the third argument, we know about Ned on the electric guitar. What do we know about the firstborn? That firstborn talked at 18 months. What do we know about Cowles? Water temperature is 55 degrees. What do we know about Ned on the electric guitar? Well, he's really good. He rocks. And then we are extrapolating that property of talking at 18 months, being 55 degrees, and being rocking to the thing we don't know about, that we're guessing about, namely the secondborn, the second surf spot, the Hook, and Ned on the acoustic guitar. Okay, let's do more examples. Let's say that the Dow Jones Industrial Index increased by 40% in the 90s. So this is a measure of how the stock market is doing. Does that mean that it will probably increase by 40% in the 2000s? Well, that's not as good of an analogy because how the stock market performs in one decade could be dramatically different, and often is dramatically different than it performs in another decade. So that analogy is weaker than some of the other ones. How about this one? Ted got an A on Ryan's logic exam, so Ned got one too. Well, just because one person in a class did well doesn't mean that another person is going to also do well. We would need a lot more information. You know, if they studied together, for instance, that would make the argument stronger. Okay, now that we've done several examples, let's talk about the parts of these arguments by analogy. So there's always going to be something that we know about. So in the earlier examples, it was the firstborn, it was Ned on electric guitar, it was surf spot 1. And that we're going to call the, that is the sample. So the sample is the thing that we know about. We know about the Dow Jones in the 90s. We know about Ted's performance on the logic exam. That's the sample. And we're making an analogy between the sample and the target. So the target in this top one is the Dow Jones in the 2000s. And the second example, it's Ned's performance on the logic exam. The thing that we know about the sample that we are guessing the target also has is the property or feature in question. So what do we know about the firstborn? What do we know about the person on the electric guitar? What do we know about surf spot 1? What do we know about Ted on the logic exam? Well, we know that the surf spot temperature is 55 degrees. We know the firstborn talked at 18 months. So all of these are the property in question. We know that the Dow Jones in the 1990s has the property of increasing by 40%. And we are guessing that the target will also share this property. What's the property in question for this latest example? Well, it's getting an A on the logic exam. So we're guessing the target of Ned also has this property that he'll also get an A on the logic exam. Okay, here's a really simple example. It's a bad argument, but it can demonstrate the parts that I'm talking about. California is awesome, so I bet Oklahoma is too. So we're comparing California to Oklahoma, right? California is the sample, Oklahoma is the target. The property in question is the property of being awesome. Okay, so these are analogies. We're comparing two things. Again, the thing we know about is the sample. The thing we're guessing about is the target. And we're guessing that the sample and target share the property or feature in question. And the strength of the argument, why we think that they share this feature or property, is because of the similarity between the two. That's why it's called an analogy. And now here's a little bit about classification. For all of these arguments by analogy, notice that the sample is never part of the target. California is not part of Oklahoma. The Dow Jones in the 90s is not a part of the Dow Jones in the 2000s, just in virtue of the fact that the 90s is not a part of the 2000s. Ted is not a part of Ned. Surf spot 1 is not a part of surf spot 2, etc. Okay, if the sample is part of the target, then we're not talking about an analogy, we're talking about an inductive generalization. So you might have noticed that the parking the first few weeks of classes is really bad in the first semester. So then you extrapolate and you think, oh, you generalize to the beginning week of every term. Right? So you notice a pattern. Oh, I've been at this school for say 3 semesters, and at the beginning of every semester, the first week, the parking's bad, and so you generalize, oh, I guess it's just bad like this every first week of classes. And you can come up with an explanation for this. You could say, well, there's more people on campus because people, everyone shows up the first week. Fewer people are skipping classes the first week. There are people maybe in more classes than they're eventually going to take. Maybe people will drop, etc., etc. Okay, here's another generalization. My last 3 boyfriends cried when I broke up with them. I bet all my BFs will be crybabies. So the sample here are the last 3 boyfriends, and the target are the boyfriends in general. The property in question is the property of being a crybaby. Notice the sample is part of the target. The last 3 boyfriends are a part of all the boyfriends. Ryan's critical thinking course is batical. I bet all his courses are the effin' shizzle. Okay, that was a bad joke. But setting that aside, we still have an inductive generalization, and we have a sample target property in question. The sample here is the critical thinking course. The target are all my courses, and the sample, of course, is part of the target. And the property in question is being good, which we put into slang either a batical or terribly the effing chisel, whatever that means. Okay, so, but notice too that, generalizations sound like generalizations because you're generalizing. There's words like every, all, the beginning of every semester, all my boyfriends, all his courses, right? Analogies usually don't do this. All right, now let's talk about evaluating analogies and generalizations. So there are 2 important things that you want to keep in mind. One of them is the sample size. You want to ask, is it large enough? Now, it doesn't necessarily need to be large, it just needs to be sufficiently large. And you might think, well, what's the difference between the 2? Well, take this example. Let's say that you have a pot of coffee, and you pour it, and you take a sip, and you notice that it's cold. Now, what is the sample there? The sample is the 1 cup. It's a sample of 1. But notice that that is sufficiently large, isn't it? Because even though it's a sample of 1, it is representative of the whole. And that's because a pot of coffee is homogeneous. It's uniform throughout. There's not a lot of diversity. But if you have a general target population that is very diverse or heterogeneous, then a sample of 1 usually won't cut it, right? So, try to think of 1 person that represents all Americans. That's really hard to do. But 1 cup of coffee from the pot could represent the whole cup. Okay, so but in general, the rule is the bigger the better, but that's not always true, as we had in the coffee example. And the second thing you're looking out for is representation, or this long word, representativeness. See, it's so long I can't even say it. But it's about representation. You want the sample to represent the target. And the way we think about representation is a little bit different for analogies than it is for generalizations. So what I want you to do is, when you think about representation or representativeness, if you're looking at an analogy, ask yourself this question: are the sample and target similar enough in the relevant ways? And if it's a generalization, just ask, does the sample represent the target? So AA there stands for argument by analogy, and IG stands for inductive generalization. Okay, let's classify these. So what kind of arguments are these? Sorry, all these titles got cut off. Every crow I've seen is black, so all crows are black. All right, what is the sample? What is the target? What is the property in question? And let's categorize it. Is it an inductive generalization or an argument by analogy? And then is the argument any good? Let's do all these sorts of things. And what this exercise that we're doing now is actually really good practice for what you're going to have to do on the exam, right? I'm going to give you short arguments like these, and you're going to have to do all the things that we're about to do. Okay, in this first one, the sample is every crow I've seen. The target is all crows. The property in question is the property of being black. The sample is part of the target. Every crow I've seen is part of all crows. And so this is an inductive generalization. Do we have representation? Is the sample size large enough? Well, that's a question mark because we don't know how many crows this person has seen. If they've seen a lot, well, then the sample size is probably large enough. And if they've seen crows in lots of different places, then that sample may very well be representative. All right, let's go on to another one. Aunt Sue got drunk at my cousin's wedding last year. I bet she'll get hammered at my wedding. The sample is Aunt Sue at the cousin's wedding last year. The target is Aunt Sue at my wedding. The property in question is getting drunk. And this is an argument by analogy because Aunt Sue at last year's wedding is distinct than Aunt Sue at my wedding, right? Or think about how they're distinct because the sample is about a previous wedding and the target is about a future wedding. Is this an analogy or is it a generalization? Well, it's going to be an analogy, just like I said. Is the sample large enough? Probably not. Just a sample of one. Does it represent the target? Remember the question should be, is the sample and target similar enough? I think we need more information because the sample is so small, and also we don't know, maybe there was a strange reason why Aunt Sue got drunk at the cousin's wedding. Maybe Aunt Sue was going to marry the cousin, right? And then someone else swooped in and married her. So that's the reason Aunt Sue, usually who is very stoic and not very emotional, maybe she was particularly emotional because the person she loved is marrying someone else. So we don't know. All right. This is a good example. So this might be a little argument that you said to yourself as we went through the formal logic part of this course. I hate math, so as soon as I saw P horseshoe Q and P or Q, I knew I hate logic. So the sample here is math. The target is logic. The property in question is being something I hate. The sample size, is it large enough? Well, it's math, right? So think about every course you've taken in math. That's a pretty large sample. And math and logic are pretty similar, so I think we have representation. So I think that's a decent argument, right? I mean, wouldn't you say that if someone had never taken the logic part of this course, and you asked, and they knew that they were bad at and did not like math, couldn't you, I mean, this isn't a logical guarantee, but isn't it likely that they might struggle with logic? Or they might not like it? And I think so. So that is an argument by analogy, and I think that it is a cogent one. All right, let's say you go to a coffee shop to study for your classes, and let's name this coffee shop Lulu's. And suppose you got bad service, and by bad service I mean by the barista, and not the cell phone service. So we got some semantic ambiguity there, right? Remember I taught you about that? Okay, so the barista gave you bad service at Lulu's yesterday, so you'll probably get bad service there every time you go to get coffee. The sample is Lulu's yesterday. The target is Lulu's every time that you've been and will go. The property in question is getting bad service. Do we have a large enough sample? I don't think so. Just because you got bad service once doesn't mean that you can generalize. This is an inductive generalization, notice, because the sample is part of the target. Yesterday is part of every time that you go to get coffee. But notice that we often make generalizations like this. So this is an example of, or this is an example we can relate to our real lives. And it is it's a sort of generalization that we make that perhaps we shouldn't. We generalize too quickly, and we're going to call this a hasty generalization. Have you ever been to a restaurant and you've gotten, you had one dish and one entree and you didn't like it, and so when somebody asks, is that restaurant any good? You generalize and you say, no, it's terrible. But you've only gone there once. You've only had one thing. Is that enough to generalize? And, maybe that tells you a little bit about the restaurant, but to generalize that all the food there is bad is too fast. And so I think that's what's going on in this coffee shop argument is, just because you got bad service once doesn't mean that you're always going to get bad service. I mean, maybe the barista that was serving you was in training, right? Maybe it was their first day. Okay, here's another one about music. I love Poker Face and Telephone from Lady Gaga's Fame Monster, so I bet I'll like the new album. Again, this is an argument that it's similar to one that you might make to yourself or that you might give to someone else. So the sample are these songs from a previous album, right? Poker Face and Telephone are singles from the Fame Monster. And so you are making an analogy to the new album. The target is the new album. The property in question is being something that you'll like. And notice that this is an analogy, right? You were comparing the songs from the previous album to the new album itself. And the sample size, no, so this is another example. The sample isn't very large, right? It's just 2 songs. But I think that, 2 songs on an album does tell you a lot about whether or not you're going to like an artist. Now, it would be better if we listened to 3 or 4 of the whole album, but, it's better than just 1. And, the representation here is okay. I mean, a lot of times if you like a former album of an artist, then you're going to like their future albums. But again, this is induction. It's not always the case. And I think all of us have had that experience where we loved an artist's, first album, but then we just hate their second or third albums, right? And sometimes what happens is you love their first album, the new album comes out, and at first you hate it, right, because it's so different. But then you listen to it, and it grows on you, and you end up liking it a lot, and sometimes even more than the first album. So I think that's a decent argument from analogy. All right, what we're going to do now is talk about how inductive generalizations relate to poles. So poles are something that we have to deal with in everyday life, especially during election time. It turns out that poles are inductive generalizations. Let's suppose that you were hired by Obama to see what the odds were of Obama winning in 2012, right? So let's say in around 2010 you were hired and Obama wanted to know if he had a shot of winning the 2012 election. Of course, we know that he did, so he probably did have a shot. Now, the long way of figuring this out is just to ask every person in America, are you eligible to vote? Are you going to vote? And who would you vote for? But that would take too much time, money, and effort. And so what political scientists do is they just take a poll. And they do this by taking a sample of the target population, which is registered voters. And they just ask, and the questions we should ask now, since we're not going to ask everyone, since we're going to take a sample, now we need to figure out how many people should be in the sample, and how do we ensure that the sample represents voting Americans. Well, now this would be a surprise. This might be surprising to some of you. There are about 300 million Americans. And you might think, oh, well, if we want it to be large enough to represent the 300 million, then we might have to ask 10% or 5% or 1%. But it turns out that a sample of just 1,500 can actually be large enough to represent a target population in the millions. So this is just something that statisticians, people who study statistics, figured out, which is surprising, very, very surprising. And if you look at the polls that you read about in the newspaper or online, and if you examine them, a lot of times their samples are 1,500 or even just 1,000. And they give us enough information to be scientific and to give us information about what's going to happen. Now, how do we ensure that okay, we got the number. We know we need to have 1,500 out of the millions of people that are going to vote. But now, how do we ensure that those 1,500 represent the entire country? Well, the easiest way to do that is to just select them randomly. We want random registered voters, right? So we could just put all the names of the registered voters into a computer and have the computer give us a random 1,500. And that way, it won't guarantee that the sample will be representative, but it will make it very, very likely. Now, if you have noticed the details of polls, you would notice that there's more information than just the statistic, that 56% of people vote for Obama. There's also what's called the error margin and the confidence level. So level got cut off there. An error margin, that's the range that you get. That's the range that the correct or the true answer is supposed to fall within. And usually, as you might have noticed, this is represented with a plus or a minus. Okay, so here's an example. Let's say that we found out that Obama is projected to get 65% of the vote and the error margin is plus or minus 3. What that means is anywhere from 62 to 68% of the registered voters will vote for Obama. So you literally add and subtract 3% and you get that range. And you want the range to be particularly small. If the range was too large, if it was anywhere from 20% to 80% are going to vote for Obama, that's not very informative, is it? So when it comes to error margins, we want them to be small, and usually we shoot for plus or minus 5 or smaller. The other part of the statistical information is called the confidence level, and this is the probability that the results are correct. Remember, this is induction. We don't have a guarantee that our answer is going to be correct, but it can be very, very likely. So confidence level, you want to be 95% or higher. Remember, Donald Trump was running for the Republican ticket at one point. And let's say we were working on the poll for him, and it turned out that the poll said he's going to get 35% of the vote. The error margin is plus or minus 4, and the confidence level is 95%. What that means is that there's a 95% chance that anywhere from 31 to 39% of voters will cast their ballot for Trump. And even though we don't have guarantees, the probability tells us enough that Trump should drop out, which he eventually did, because there is an extremely good chance that he's not going to get anywhere close to the majority required to move on to the general election, right? So that's what's great about induction, is that you might think, well, why don't we always just do deduction, right? The logic of certainty. Well, because deduction isn't always an option, and induction can be easier and quite powerful. Very informative. So as I said, we want the confidence level to be 95% or higher, and we want the error margin to be small, plus or minus 5 or smaller. There's a relationship between these two parts of the polls, and it turns out that the larger the sample size, the greater the confidence level, and the smaller the error margin, which I think makes sense, right? So if you have a larger sample size, the more people you ask, the closer you get to 1,500 and the more you go beyond that, the better your results are going to be. You're going to be more confident in those results, and your error margin is also going to be smaller. And the more representative your sample size is, same thing. You're going to have a better confidence level and a smaller error margin. Okay, so we talked about the random sample. There's also a relationship between confidence levels and error margins. As your confidence level goes up, what do you think is going to happen to your error margin? It's also going to increase. So the more confident you are, the larger the margin of error is going to be. And the less confident you are, the more you can shrink your error margin. I think an easier way to remember that is, let's say that you artificially increase your confidence level. Well, increasing, there's a give and take, right? If you're not increasing your sample size or representation, if you're just messing with the confidence level without touching those things, then if you do one thing that's good, it's going to cause something that's bad, right? So if you increase your confidence level, that's good. Well, that's going to do something bad to your error margin, and that means your error margins can get larger and larger, which is bad. And vice versa. If you do something good, or if you do something bad to your confidence level, which is decrease it, then that's going to do something good to the error margin, which is shrink it. All right, let's talk about some fallacies that are related to arguments by analogy and inductive generalization. Well, if the sample doesn't represent the target, or if the sample and target aren't similar enough, then you have a biased sample. And we'll go through some examples in a second. The other fallacy is when the sample isn't large enough. We call this a hasty generalization. And a subspecies of that, a specific kind, is called the fallacy of anecdotal evidence. And that's when your sample size that's too small is really just a story from your personal life. And then finally, I'll give examples of all these in a second. And then finally, we have the gambler's fallacy. And that's when you are just confused or wrong about the odds, right? It's really when you think the odds are anything than what they are, what they in fact are. Okay, so now let's go through these examples and practice these fallacies. So if I said the vast majority of people who live in Santa Cruz would re-elect Obama, does that mean Obama's probably going to win in 2012? Is this a biased sample, a hasty generalization, anecdotal evidence, or a gambler's fallacy? Well, it turns out that it's a biased sample because people that live in Santa Cruz typically lean left, and so they don't represent the country as a whole, so the sample is biased. You might say that it's also a hasty generalization, but this would not be the case at all because if Santa Cruz has 50 or 60,000 people, so if you have the majority of that, you're going to have 25 or 30,000, and that's way above the 1,500 that are required. So it's not a hasty generalization, it's a biased sample. How about this argument? When we played basketball, I made my first shot, so I'll probably make them all. That's definitely a hasty generalization. Your sample size is 1. And it also could be a biased sample because that first shot may have been really close to the basket, and that doesn't necessarily represent all your shots, which could be much further away. So a lot of times it can be multiple fallacies. In this case, it's both a hasty generalization or a biased sample. It was cloudy the first day of the month, so it'll be cloudy the first day of every month. Again, the sample size is too small and it's biased. My grandma smoked until she was 90. No lung cancer. So I'm going to start smoking cigarettes. I don't have to worry about this. This is the fallacy of anecdotal evidence. Which is a kind of hasty generalization. But notice the sample size here is from our personal experience, right? Alex Rodriguez hasn't gotten a hit in 2 games. He's due. This is an example of the gambler's fallacy because whenever a batter goes up to bat, the odds are never in their favor of getting a hit. Presumably, when you say he's due, that means that the odds are good that he's going to get a hit, right? And good meaning, I don't know, greater than 30%. Certainly, greater than 50%. Certainly greater than 40%. But if you know anything about batting averages, which represent the odds that you're going to get a hit when you go to bat, they're never in the positive. They're never in the majority, right? Some of the greatest hitters of all time, have barely gotten to a batting average of 40%, right? And a batting average of 400. Usually, a good batting average is over 300, but that's only a 30% chance. About 1 in 3 times you get a hit. So you're never due to get a hit when you go up. So the odds are, less than 40%. You think the odds are greater than 50. So that's the gambler's fallacy. Arizona has tougher immigration laws, so the rest of the U.S. should follow suit. So is this a hasty generalization? I don't think so. The sample size is just 1, but we only have 50 states, so that's not too bad. I mean, it's a little bit bad sample size, but it's not too bad. This is just much more of a biased sample because Arizona is a border country, and that's a very different circumstance than, say, Kansas or, say, Connecticut, right? Going to have different needs when it comes to immigration. I can sing naked in the shower, so I can sing naked in the street. This is an argument by analogy. The sample is being in the shower, the target is being in the street, and the property is being able to sing. this is a bias sample, right? There's not a close enough relationship between how you act in the shower and how you act in the street. One's a very private place and one's public. So it's a bad analogy because there's not a good similarity between the sample and the target. So we have a bias sample. All right, the roulette wheel has hit black 7 times in a row. I'm going to bet on red. This is a classic gambler's fallacy, right? So if you move your bet from black to red, then presumably you think that the odds are better for red than black. But this is never the case. In roulette, the odds, whether it's black or red, are always the same. And you think that the odds for red are better, so you're being mistaken about the odds. That's the gambler's fallacy. All right, the last thing we're going to do is apply some of this to philosophy. There's a famous argument by analogy from a philosopher named William Paley, who was a famous theist. He tried to prove, well, not prove, he tried to give an argument, a logical argument for the existence of God. And it was something like this. Watches, and we're talking here about complex systems, are intelligently designed. That's premise 1. Premise 2 is the universe is an infinitely complex system. Conclusion, therefore, the universe was created by a designer with infinite intelligence. And that intelligent designer with infinite intelligence, Paley defined as God, right? So then we've got the existence of God. So there's an assumption here that as the complexity of something goes up, the intelligence of the designer behind the complexity must always go up. And maybe that's a fair assumption. We could question that, but we'll grant Paley that. But another way to think about this argument is, suppose to make an analogy between the universe and a book. It would be nonsensical for a book to have no author. And so extrapolate that to the universe. It doesn't make sense for the universe to have no creator or no author. Okay, so let's treat this by an argument from analogy. There's got to be a sample, a target, a property in question, and then we can evaluate it based on representation, similarity between the sample and target, and the sample size. So what is the sample? The sample are watches or complex systems. The target is the universe. The property in question is the property of being intelligent designed. So we know watches are intelligently designed, and we're guessing that the universe is intelligently designed. Okay, so is this an analogy or is it a generalization? Well, this is an interesting one because watches are part of the universe. So you might say this is a generalization, but usually this is typically thought as an analogy because it's a comparison between watches and the universe. But I mean, if you want to think of it as generalization, that's fine too. I mean, we could stick to our rule and be consistent, that's fine. The classification doesn't matter so much. But a lot of people think this is an analogy because of the comparison between watches and the universe. And it doesn't sound so much like a generalization. All right, the sample size is 1, or multiple. We're talking watches, there's many watches. And if we go to complex systems, then we have a big sample size, right? Because computers and calculators and machines are all complex systems, and they all are intelligently designed. Okay, so we won't have a hasty generalization. But whether or not this argument works is going to depend on the similarity between watches and the universe. And so a lot of people will say, well, this doesn't quite work because watches are one thing, the universe is different, right? There's another objection here that from David Hume, who's a famous Scottish philosopher. He argued that to really know that the universe is complex, or to know that it looks like it is designed, we would have to be able to compare it to other universes, right? This is the only universe we know, so it's a little bit short-sighted to assume it's designed. If we knew about a plethora of universes, let's say we knew about 10 universes, we could kind of look around from universe to universe and compare them and then say, oh yeah, this one's super designed. In that other universe, everything is messy and there's not harmony, there are no laws of nature. But we don't have access to other universes to compare. So, maybe, let's say there are other universes, and maybe they're way more designed than ours, and we only think ours is designed because we don't know any better. So that's an argument Hume has. Also, Hume says there are lots of counterexamples. There's lots of things that are complex but not intelligently designed. He gives an example of a snowflake, right? If you put a snowflake under a microscope, you can see intricate complexity, right? But he says, no, a snowflake's just kind of formed by nature and doesn't have to be designed. And then another point from a critic of this argument might say, we are anthropomorphizing or personifying the universe, right? We're just so used to living in our little bubble where all these complex things are designed, and we generalize, or we're making this comparison that the universe must also be designed. But, why does it have to be? I mean, it could be that, these complex things that we make are designed, but then when it comes to the universe as a whole, it's just not. It just kind of either plopped into existence, after the Big Bang, something from nothing, which is problematic in its own right. Or perhaps the universe just always existed, sort of like numbers. They just go, they go on and on forever. Maybe the universe goes on and on forever in terms of the past, and it didn't really come from anything. I mean, that could be. Anyway, so I didn't really bring this up to show that Paley was wrong or that he was right. It's just a cool way to show that what we're doing in logic, this inductive logic, actually has applications to real life and to philosophy. Okay, hope you really enjoyed that, and we're almost done. One more lecture to go.